In this video, we cover how binary search trees work. For an overview of what binary search trees are, watch my last video. As a brief recap, trees are made of nodes. Nodes contain data, and they can point to other nodes. Binary search trees have two additional restrictions. First, each node can point to at most two other nodes. Second, all child nodes to the left must have data less than the parent nodes, and all child nodes to the right must have data greater than the parent nodes. There are three main operations that can be done with binary search trees: adding nodes, searching for nodes, and removing nodes. We'll start with adding new nodes. To add a node, we first start by finding where the node should go. We start at the root and compare the two values. Here we want to add 3 to the tree. Since 3 is less than 5, we go left. We then compare the node value and the target value again. Here 3 is greater than 2, so we will go right. However, there is no node to the right. Once we find that there is no node in the direction we want to go, we have found where the new node should go. Instead of moving, we insert the node. We repeat this process of searching and insertion for every element we want to add. Each time, we start at the root and search for where the node should go. Once we find the correct spot, we insert the new node. The next operation is to search the binary tree for specific nodes. Searching for nodes is very similar to adding nodes. We start at the root and compare our target number, 12, with the root's value, 5. Since 12 is greater than 5, we move right. We then compare 12 with the next node's value, 10. Since 12 is greater, we move to the right again. We then compare 12 with the current node's value, which is also 12. Since both our target and current node are 12, we have found the node. Now let's search the tree for the number 4. We start by comparing 4 with the root, which is 5. Since 4 is less than 5, we move to the left. We now compare 4 and 2. Since 4 is greater than 2, we move to the right. We now compare 4 and 3. Since 4 is greater than 3, we try to move to the right, but we see that there is no node there. Since there is no node, we know that 4 cannot be in the tree, so the search says that 4 is missing from the tree. The next of the main operations is removing nodes from the tree. Removing nodes is the most complicated operation and has 4 different strategies. The first is the leaf strategy, where the target node has no children. The second strategy is the redirect strategy, where the target node has 1 child. The third strategy is the successor strategy, where the target node has 2 children. Then there's the successor redirect strategy, which combines strategies 3 and 2. We'll begin with the leaf strategy, which is used when the target node has no children. Here we'll remove the number 3 from our tree. Just like other operations, we start off at the root and try to find our node. Once we find the 3 node, we check how many children there are. Since 3 has no children, we do the leaf strategy. The leaf strategy is simply to delete the node from the tree. Now let's do the redirect strategy, which is when the node has 1 child. For this example, we'll remove 2 from the tree. Start at the root and do our comparisons to find the target node. Once we found the target node, we check how many children it has. Since the 2 node has 1 child, we cannot simply delete the node. If we did just delete the 2 node, we'd also delete the 1 node. Instead, we have to redirect the 5 node to point to the 1 node, and then we can delete the 2 node. This redirect makes sure we only delete the node we want to, and we don't delete any other nodes. Finally, we have the successor strategy. The successor strategy is the most complex of the removal strategies, since we do 2 searches. The first search is for the node we want to remove. The second search is for the node that will take the place of the removed node. For our example, we'll remove node 10. We start off by searching for the 10 node. Once we arrive at the node we want to remove, we start the second search for the successor. The successor node is the smallest node that is also greater than the node we want to remove. If you want to figure out how to find the successor node, go ahead and pause the video. We find the successor node by going to the right once and then going as far left as we can. In our case, the successor node is the 11 node. Once we have our successor node, we replace a removed node with the successor. Since we used the smallest node larger than our removed node, all nodes to the left are still smaller than the successor node. while all nodes to the right are still larger than the successor. This means that we've preserved the ordering restrictions of our binary search tree. However, there is one edge case that we need to address. What if the successor node has children? If the successor node has children, then we need to make sure its children stay in the correct spot in the tree. Otherwise, we risk losing them or getting nodes out of order. To do this, we use the fourth and final strategy, the successor redirect. The successor redirect combines both the successor strategy for our target node and the redirect strategy for our successor node. For instance, let's say we want to remove the node 11. We start off doing the successor strategy with its two searches. The first search to find our target node and the second to get the successor. However, here the successor has one child node. To handle this case, we now do the redirect strategy on the successor node. The redirect strategy redirects the parent node to point to the child node. Now that the child node is still in the tree, we can finish the successor strategy by replacing 11 with 12. In my next video, I will walk through code examples for binary search trees and demonstrate how they work.